I'm Jack Francis. I work at Microsoft on open source Kubernetes.
And I'm Jason Deal. I'm an engineer at AWS, and I work on Karpenter, among other open source Kubernetes projects.
Before we get started, I wanted to call out everyone who contributes to SIG Autoscaling. So the first point of business is to say thank you to everyone who contributes. Prior to this talk, we heard from SIG Auth, and I'm jealous they have 6 tech leads and chairs among them. We have 3 active, which means that across the vast diversity of stuff that we're responsible for, it is largely community volunteer curated and maintained. So we're really, really grateful for that. Just a brief, again, I'm Jack, I work at Microsoft. Jason's on Karpenter at AWS. And we are going to give a high-level overview of autoscaling across a few dimensions. And then we're going to go pretty deep with Karpenter, which is going to be exciting. And we're going to tie project updates together through a sort of DRA lens. And then we'll give you a brief state of the ecosystem, how to get involved, and we'll have time for Q&A, hopefully. So SIG Autoscaling, at an introductory level, what we are responsible for is cluster and in parentheses node autoscaling. So that is handled by 2 projects, Cluster Autoscaler and Karpenter. And additionally, workload autoscaling, which I've got pod in parentheses there to bring that down to a more concrete level. And for that, there's horizontal pod autoscaler, vertical pod autoscaler, and a very old but venerable project called add-on resizer. And I've got this fun slide in the middle to kind of hint, and I apologize for the lack of animation. Speaking of venerable, everybody knows that image. We are actively working across SIG scheduling, SIG node, device management working group on a set of frontier concepts that will bring in something like workload autoscaling, device autoscaling, and topological autoscaling. So if you're interested in this, please reach out to ourselves in the autoscaling SIG or any of the other SIGs and get involved in those discussions. That will be coming soon. Okay, I'm going to quickly talk about Cluster Autoscaler and Karpenter. So Cluster Autoscaler is a component that runs in your cluster that monitors pending pods and increases node pool replicas in response to a need for more pods. It also will recognize when nodes are not sufficiently dense or completely empty and remove those underutilized nodes. And the way that it does this is by performing proactive simulations of more or fewer nodes compared to the actual cluster, and then carries out those infrastructure addition and removal requests. Karpenter monitors for pending pods similar to Cluster Autoscaler, but a key difference between Karpenter and Cluster Autoscaler is that Karpenter is actually a provisioner, and it provisions infrastructure from scratch to meet the needs that the workload declares. Jason will go into great detail there, but similarly, it can go up or down or out or in depending on the state of your cluster dynamically. And I mentioned there, it supports all the standard scheduling constraints for node selection. Very brief overview of horizontal pod autoscaling. So horizontal pod autoscaler is an in-tree mature Kubernetes API. It increases and decreases pod replicas to achieve a particular target. So typically there's a metrics trigger that will actuate an addition or decreasing of pod replicas. And as you might be able to infer, HPA is the canonical way to trigger autoscaling events on Cluster Autoscaler and Karpenter. So essentially you have an HPA that looks for pod utilization and can create more pods in response to increased utilization or decreased pod count as utilization goes down. Vertical pod autoscaler is a component that does something similar in terms of monitoring for utilization, but rather than creating more pods, it makes your pods bigger or smaller. Vertical pod autoscaling is a separate component with its own release cycle, so it's not built into Kubernetes, but it is very actively maintained and widely adopted. Okay, I'm going to pass it over to my colleague Jason here.
Okay, so we wanted to just go through a few of the major Karpenter project updates that we've had over the past year or so. So, trying to see if I can get this taskbar to disappear. Okay. So, for those who aren't aware, we graduated Carpenter's core APIs, those being the Node Pool and Node Claim API to V1 back in August of 2024. So, those two core APIs, which are shared across all cloud providers that implement Carpenter, are now considered stable. And as such, a lot of our focus in the upstream project has been on performance enhancements and enhanced benchmarking. But there are still a few major features that I wanted to highlight today that we have shipped since that V1 release. So the first one I wanted to talk about was reserved capacity. So for those who have used Carpenter, you might already be aware that there were two existing capacity models, those being on-demand and spot. And these map pretty closely to the different purchase options that you have in different cloud providers. On-demand is generally going to be the capacity that you pay for it as soon as you start using it, and you can continue using it until you choose to terminate it, or in this case, when Carpenter chooses to terminate it. Whereas Spot is going to be typically a discounted capacity model, but the cloud provider could reclaim that capacity at any time. So we had this two different capacity selectors that you could use for on-demand or Spot, depending on what your workload was tolerant to. If you had, for example, a workload that isn't tolerant to disruptions, you might not want to run it on Spot capacity. But if you have workloads that can be tolerant to those disruptions, you may want to opt in. That way you can save a decent bit of money. But neither of these models really help with modeling pre-purchased capacity. And there are a number of reasons you might want to pre-purchase on-demand capacity. Potentially you need instance types that are a little bit capacity constrained, and you need to ensure that you have enough for your workload ahead of an event. So that might be a reason that you pre-purchase it. And with Carpenter before, there were a couple of approaches to kind of model this. So I'm going to run through an example where you have a capacity reservation of, say, 50 C5 large instances in one specific zone. I'm using AWS specific instances just for the sake of example, but you could swap this out with any cloud provider. So what our ideal behavior would be is we want to consume all of those pre-purchased instances before we start falling back to a general set of instances that we have to purchase on the fly. And one way you might go about trying to do this in the previous model is you have a higher weight node pool with that specific instance type, and then you have a lower weight node pool that's more open. And the idea would be that you continue to provision instances in that higher weight node pool until you can't anymore, and then you fall back. So this works okay, but you're going to continue to provision those C5 larges in that specific zone until the cloud provider tells you you can't anymore, which potentially is going far past your actual reservation limit. So sometimes that might be okay, but often you might want to fall back a little earlier. That way you ensure you're getting the best instance type for your workload, not just this instance type that you chose to pre-purchase. So you can approximate this a little bit by setting CPU limits. So that's the only difference between those two examples. It's in this first node pool. You have a CPU limit of 200. C5 larges have 4 vCPUs. CPU limit of 200 gets you to 50 instances. So once 50 instances are provisioned for this node pool, you're going to fall back to that second node pool, which is more general. So this works okay, but makes a couple of critical assumptions. One is that you're only using this pre-purchased capacity in this cluster. And the other is that it's also only being used in this node pool. And sometimes that might just not match the model that you're trying to use for your pre-purchase capacity. So that's why we went ahead and introduced a new capacity type called reserved. So this joins on-demand and spot as the third pillar of capacity types in Carpenter. And the idea is that now each instance type offering, so an instance type offering in Carpenter is the combination of the instance type and the zone it's available in. Each reserved offering for an instance type is going to have an associated capacity that is populated by the cloud provider. So in the case of this example, that would be 50 at least to start, but let's say another cluster or some other source consumes some of that capacity. That count inside that offering is going to be live updated. And with these reserved offerings, we've actually updated Karpenter's scheduler to ensure that all of these reserved offerings are completely consumed before falling back to on-demand and spot. So this is an example of what, with the new reserved offering mode, this would look like today. So you can see we've went from 2 node pools, one for fallback, one for the reserved offering, to a single node pool. That node pool now has 2 capacity types, on-demand and reserved, and it's just open in general. So it's very generalized. It happens to capture that pre-purchase capacity, but it also captures a swath of other instance types that you may want to fall back to if they're more appropriate once you fully consume that pre-purchased capacity. So the method of actually understanding how much capacity is available for any of these reservations is going to be very cloud provider dependent. I did include a node class definition, which shows how you might do this in the AWS provider, but know that this might be different in, say, the Azure provider or any other providers that choose to implement reserved capacity. So here we have just a mechanism to select a set of on-demand capacity reservations. So that's about it for reserved capacity. This feature was introduced in Karpenter v1.3, which was about in March this year, and it graduated to beta in v1.6. So the second feature that I wanted to talk about is a feature called Node Overlay. So to set the stage for why we kind of needed this feature, Karpenter is what we call a scale from zero autoscaler. So basically, most of the time when we are launching a new node into the cluster, we don't have a node in the cluster to use as a template because we might be using an instance type that isn't in the cluster yet. Because in AWS's case, for example, we're selecting from, say, 750 instance types. I don't know where the Zoom call is coming from. Okay. So, we rely on different cloud provider implementations to tell us about the pricing for each of these instance types and also the resources that will be made available for these resource types so we can simulate what the node will look like before we choose to scale it up and so we can ensure that it's going to work for the pods that we're trying to provision a node for. The problem with this is that some of the information can really only be known by end users. So this includes things like third-party licensing deals for pricing, potentially like OS licensing fees or daemon set licensing fees. And also for extended resources, there's a swath of different device plugins. Karpenter is only going to natively support some of them. So we wanted to introduce a mechanism to allow users to use extended resources from any arbitrary device plugin. So this is kind of what that looks like. This is an example for how you might go about doing a pricing override. So Node Overlay is a new CRD that's introduced in upstream Karpenter, and it basically is made up of 2 components. It's made up of a selector, and it's made up of some type of adjustment. So here we can see that we have a requirement saying we want this node overlay to be applied to any node that is provisioned for node pool foo or node pool bar, and we want to adjust that price by $1. So increase the price by $1. And you could imagine the use case for this being like those OS licensing or daemon set licensing fees. So there's both options for doing relative adjustment and absolute price overrides depending on your use case. And this information is both utilized by provisioning, so determining which instance type is most cost effective when scaling up, and consolidation for determining how much money will we actually save if we remove this instance type, or provision this instance type to replace a different one. And this is just another example of what this looks like for capacity as opposed to price. So you also have this capacity field where you can set any number of extended resources. And you have that similar selection mechanism. So in this case, we went from node pools to selecting on a very specific set of instance types. And here we are setting this custom hardware accelerator for those instance types. And now Karpenter, when it sees a pod that comes in with a request for that resource, will know that any of these instance types can fulfill that request. So the final feature that I did want to highlight was static capacity. This is a feature that just came out, I think, in Karpenter v1.8, so currently in alpha. But this is a new feature that allows you to maintain a fixed number of nodes with Karpenter as opposed to only relying on reactive autoscaling. So the actual API update for this is okay, so the actual API update for this, once we get back to it, is pretty straightforward. There is just a new replicas field on the node pool. And semantically, what this does is we are going to create that number of replica nodes that match that node pool, and we are going to maintain that capacity. So this is ideal for potentially static workloads or workloads with low latency requirements that you want to ensure that you scale up capacity ahead of time. And the advantage of using Karpenter for this as opposed to, say, like manually adding nodes to your cluster is you still retain all of the Karpenter configuration you may be familiar with, and you also get some of the other benefits of Karpenter's node lifecycle. For example, you get drift for automatically updating all of your nodes. So with that, I think I will hand it back over to Jack to talk about the cluster autoscaling project updates.
Thank you, Jason. Thanks for dancing around some PowerPoint issues. All right, so this is gonna be a somewhat filtered list of things to focus on in the last sort of 6 months since the last KubeCon. I wanted to emphasize a couple of things in HPA and VPA. In HPA, custom tolerance for HPA has now graduated to beta. In 135, custom tolerance allows more fine-tuning for HPA configuration. And in-place pod vertical scaling graduates to GA in 135, which is great news for Kubernetes in general. And then VPA integration has been there since 1.4. So expect that to be mature. And I also want to talk through some of the DRA updates that are happening in Cluster Autoscaler. So we actually announced, I think last year, around 132. Since then, structured parameters, which is the basic set of 132 vintage DRA functionality, that has been supported in the equivalent Cluster Autoscaler 132 releases and later. With 133, we brought additional optimizations around DRA and node readiness, and a bunch of operational optimizations in the Cluster Autoscaler simulation code itself. And there is a lot of ongoing work in the Cluster Autoscaler to integrate partitional devices, admin access, non-binding conditions, and we also have some forward-looking work for integrated nominated node name, which is going to be beta in 135. And there's also a to-do item for DRA-enabled daemon sets and DRA-enabled static pods. So I know that was like a super rapid-fire summary of features that you go into a lot of detail. I'd be happy to answer any questions, or feel free to get involved and reach out to us at the SIG. Additionally, this is more forward-looking. So as I mentioned, the custom tolerance and in-place vertical scaling has graduated in 135. There is a buffers API proposal that landed over the summer, and that is going to be integrated in 135, so that's ongoing in Cluster Autoscaler. So it's an autoscaling specific API that enables static capacity to be added as input to autoscaling like Cluster Autoscaler. We are also tracking KEPs in SIG scheduling and storage for integrated volume limits. And if you're following any of these KEPs, we're working on this in Cluster Autoscaler in particular. So there's a node readiness gate SIG that spans node, scheduling, network, and storage, which is going to be a feature that can be consumed by Cluster Autoscaler for better scale out and scale in behaviors. And there is also a new KEP for pod conditions for node autoscaling. So that's going to bring, as a first-class condition, standard autoscaling conditions into the pod spec itself. And then there's also a fallback for HPA when metrics fail. That KEP is actively being developed for 136. Okay, I'm going to pass back to Jason. He's going to talk about Karpenter and DRA.
Okay, so Karpenter with DRA, we don't currently have any support for DRA, but this is something that we are actively developing. So to give you an idea of the scope that we are targeting, the initial targeted support is going to be that initial set of structured parameters functionality that Jack had just talked about. Of course, with all of the other features that are coming to DRA, that is something that we will be looking into once this initial set of functionality gets implemented. As far as structured parameter support in Karpenter, there are really three core components to this. The first is going to be how do we discover for any arbitrary instance type what resource slices and what devices will be available for that instance type. So this kind of goes back to that whole scale from zero issue I was talking about with node overlay, where we need some way either for the cloud provider to inform us or for the end user to inform us of what these devices are going to look like for any given driver. The second part is going to be actual integration into our scheduler, which I'll talk a little bit more about in a moment. For those who aren't familiar with Karpenter's internals, Karpenter has its own scheduling implementation, which is slightly different than how Kubescheduler works. So we'll talk about that a little bit more in a moment. But then finally, we have the integration into Karpenter's node claim lifecycle. So as far as where we are at today, we've had some different mechanisms for doing resource slice discovery that are in review. So if you're interested in any of those, I would encourage taking a look at the RFCs that are in the upstream Karpenter repo. Scheduling integration is also in progress. This is something I'm personally actively working on. Nothing published yet, but hopefully we will see some movement there soon. And then we've also made good movement on the testing integration with Karpenter's Qwak provider, which is a custom cloud provider implementation we made upstream so that we could test Karpenter's core algorithms in a cloud provider agnostic way. So to kind of give a brief overview of what DRA looks like or will look like in Karpenter, and kind of just an overview of what Karpenter's scheduling simulation looks like in general, I have this diagram. This is a high-level view of what Karpenter's scheduling simulation looks like. So basically, we have a bunch of pods that are pending. Kubescheduler has marked them as unschedulable. So we know now, okay, we need to provision some new nodes for these pods. As long as we are able to progress, we will try to first schedule a pod to any existing node in the cluster, just make sure there's no race conditions with Kubescheduler. But once that fails, we get to the two interesting steps where for the first pod, there aren't going to be any in-flight node claims. So we go right to creating a new node claim based on one of the node pools in the cluster. And the way that node claim creation works is basically we take the template that you define in your node pool, and that is the base of any node we create. And then each time we try and add a pod to that node, we tighten the constraints on that node claim such that we guarantee that that pod will be able to schedule to whatever node is created for it. So this might look like tightening topology constraints, potentially like eliminating zones that the node claim could be created in, stuff like that. Or updating the resource requirements. If your pod has so many CPU requests, so many memory requests, etc., we add that to the requirement of the node claim. So that's what we do when we create a new node claim. And then every time we try to schedule a pod to an in-flight node claim, we do a similar process where we look at all of the node claims we've already created for pods in memory and see, okay, can we add this pod to that node claim, tighten its constraints, ensure it will schedule, and ensure there are still instance types that can satisfy that node claim. And once we've gone through all of the pods, or we've figured out that we can't make any more progress for any of the pods, then we finally go and create all of those node claims, and then the node claim lifecycle that we'll talk about in a moment kicks in. So what needs to be extended here for DRA is now we're no longer just concerned about node claims and like the topology requirements that they have and the resource requests associated with them, because now we have this whole other set of devices that we need to be scheduling against. So you can imagine that now, instead of just looking at the node claims, we're also looking at all of the existing resource slices in the cluster, and all of the potential resource slices that could be created for each instance type. So that's kind of where we're heading with scheduling. As far as the node claim lifecycle integration, Karpenter's node claim lifecycle has 3 phases today. Those being launched, which is after we create the node claim, has the cloud provider successfully created an instance to satisfy it. Registered, which is once the kubelet running on that instance successfully registers a node with the cluster. And then finally initialized, which among other things, checks to verify that all extended resources have been published to the node. So you can imagine with the conventional device plugin method, there could be some latency between the node being registered and all of the extended resources like your GPUs being published to the node. So we wait for all of those to be published before we mark it as initialized. And that is the main thing we're going to be extending for DRA, because we need to now not only ensure that all of the extended resources have been published, but all of the extended resource slices have been published to satisfy the requests that we expected for the node claim. And this is a little bit trickier than extended resources, because with extended resources, it's as simple as checking, does a string match and does a number match? Whereas with resource slices, it's a little bit more complicated because there can be arbitrary information like serial numbers as attributes, stuff that we can't necessarily know ahead of time. So we're going to have to develop this semantic equality check to see, does a resource slice look close enough to what we envisioned for us to consider it initialized? So yeah, that was a brief overview of kind of where we're looking with DRA. So I will give it back over to Jack once again.
Yeah, we're almost out of time, so we'll go really quickly. But I want to emphasize that the ecosystem around both Karpenter and Cluster Autoscaler is continuously growing, and in particular around Karpenter, we have a bunch of new providers that are worth talking about. So we have AWS and EKS, and then EKS Auto Mode. That's maybe where you would expect to see Karpenter. But we also have Karpenter running AKS's auto node provisioning. We have official IBM and cluster API providers that have been donated to the SIG, so we're really excited about shepherding those going forward. And we see a rapidly growing community maintain provider ecosystem around Karpenter. There's a few examples up there, but it's larger than that, and subject to change. Maybe someone's creating a new provider right now as we speak. In Cluster Autoscaler, GKE has, I'm going to list 3 of its sort of autoscaler options. So it has a Cluster Autoscaler feature when you create a GKE cluster. You can also use custom compute class, and you can also use node pool auto creation. All of those are, Cluster Autoscaler underlies all of those GKE autoscaling options. In AKS, the Cluster Autoscaler feature is still available and supported. That's underlined by Cluster Autoscaler as well. And then from an open source perspective, there are at least 33 active providers in the ecosystem. And just in the last few months, there's a new provider from CoreWeave and a new provider from Utho Cloud, which is an Indian, a cloud in India. And if you would like to get involved, well, before I say that, I wanted to especially shout out to Ray and Maciek, who have retired from tech lead duties in SIG Autoscaling, and hearty welcome to Adrian Moisey, who is not able to come to Kubecon, but he's a new tech lead for VPA in particular. And we want everyone here and anyone listening to the recording to please join. This is Karpenter specific. Jason, you want to make a quick mention of this?
Sure, yeah. I think the best place to get involved would, if you're interested in talking with maintainers, we have bi-weekly working group meetings and issue triage meetings. If you follow that Google Calendar link, once we publish the slides, you'll be able to find all of the calendar invites for those. You can also find them on our GitHub and our README. Of course, always welcoming issues and feature discussions in our GitHub. And then we also have 2 Slack channels in the Kubernetes Slack, so both #Karpenter dev. As the name implies, one is more end-user focused and one is more development focused, but please feel free to get involved there.
Yeah, and similarly for SIG Autoscaling generally, there's a mailing list that you can join. It's not super active, but And we also have a Slack, which is very active. Weekly community meetings on Thursdays. So I've included the Pacific U.S. time zone, GMT, and Central European time zones there, and a link to the community calendar. And you don't have to do any of that. You can simply just open an issue or submit a PR. Very, very welcome to do that. We might have a minute for questions or so. We also, I think, don't have anyone trailing us. So if we want to just do ad hoc questions, both of us would be super happy to answer questions. Please leave feedback on how to better manage PowerPoint slides in a large audience at a recorded meeting with that QR code. Thanks, everybody.